scientists could regard the debate as fruitless. This typical timorous approach, characteristic of Western attempts at scientific education, hardly can be conducive to efficient scientific development. There is no time independence. This is first-grade stuff, and there is no point in being indecisive about it. Ever since Einstein's special theory of relativity, the idea of time independence has been defunct. Remember, under inseparability, we considered space as matter and time as motion. Even Minkowski hinted at this in his famous statement of 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Irreversibility and the environment of the system. In the deterministic view, absolutely no reaction or event occurs independent of time, because time is motion. The terms reaction and event are terms describing motion. No reaction or event is reversible in the absolute sense, because the material objects in the environment in which it takes place are in continuous motion. Each star, each galaxy moves relative to all the others. The night sky is unique each time we view it. Reversibility could only occur in systems that are completely isolated from the rest of the universe. Such isolation is impossible, and therefore reversibility is impossible. The seventh assumption of science, irreversibility, asserts that all processes are irreversible. We need not delude ourselves into thinking that there are some exceptions involving ideal equilibrium or relative size. The eighth assumption of science, infinity. The universe is infinite, both in the microscopic and the macroscopic directions. The universe is either infinite or finite. It is, of course, impossible to know for sure which of these possibilities really exists. We can only assume one or the other. Whenever someone claims to have found the edge of the universe, someone else is free to hypothesize objects beyond. Experience in particle physics and astronomy teaches us the utility of the eighth assumption of science. And yet, each time a supposed limit is reached, the absence of data allows a choice between infinity and finity, its opposite. As I have mentioned, two very different scientific approaches have vied for the title of the scientific worldview: classical mechanism and systems philosophy. Classical mechanism emphasized the external interactions of its model. Systems philosophy emphasized the internal interactions of its model. In the evolution of the 2 points of view, the invention of the glass lens was both symbolic as well as instrumental. If the telescope was the tool of classical mechanism, the microscope was the tool of systems philosophy. The more one saw of the macroscopic world, the more one was impressed by its immensity. The more one saw of the microscopic world, the more one was impressed by its inexhaustibility. Unfortunately, the more one looks in one direction, the more one learns about that direction and forgets about the other. Classical mechanism and systems philosophy developed two different views of infinity, macroscopic and microscopic. Macroscopic infinity and classical mechanism. Although philosophy contains numerous allusions to the possibility that the universe is infinite in both the macroscopic and microscopic directions, this has always been a heretical view. The macroscopic infinity proposed by Democritus and other atomists gave way during the Middle Ages to the practical demands of astronomy and religion. In tune with the widespread techniques developed in oceanic navigation, Ptolemaic cosmology invented the theory of the two-sphere universe in which the fixed sphere of the Earth was surrounded by a moving celestial sphere. This explained the obvious rotation of the night sky about the North Star and allowed for the fantastic heaven beyond. Thus, when Giordano Bruno resurrected the theory of an infinite universe, he was, in effect, challenging the notion of an actual physical existence for paradise. This would not do. The reaction by the Church was swift and terrible. Eschewing a Galilean-type recantation, Bruno was burned at the stake in 1600. 9 years later, Galileo's telescopic observations accelerated an enumeration remarkable for its unceasing ability to furnish evidence for Bruno's speculation. With the telescope, one could study the interactions of astronomical bodies. One need not be bothered particularly by questions concerning the constituents of those bodies. Thus, it was logical that Newton's later development of mechanics would pursue this obsession with the external as opposed to the internal. Like Bruno's less pious version of infinity, Newton's was macroscopic, not microscopic. Theirs was a vision of an infinite number of solid bodies in an infinite volume. But both retained the legacy of atomism, which, without a doubt, presumed microscopic finity. Classical mechanism made its settlement with infinity in the traditional way, by neglecting and thereby finalizing and finitizing the insides of its model. Thus, when Newtonian bodies collided, the irreversible effects on the internal motions of those bodies were not understood and had to be ignored. Newtonian bodies had permanence consistent with conservative, non-evolutionary views of society. Classical mechanism was a bitter pill, but it could be swallowed. Microscopic infinity and systems philosophy. For more than half a century, almost no one thought to turn Galileo's telescope around and look inward instead of outward. Then, in 1665, Robert Hooke's observations of the cellular structure of cork initiated a search which, like Galileo's, has never failed to provide evidence for microscopic infinity. The pace of discovery in this direction, however, continued to lag behind that of the macroscopic. For instance, as early as 1683, Anton van Leeuwenhoek reported some causal observations of what only could have been bacteria, but these were not to be observed again for at least another century. A worldview that included microscopic infinity among its basic assumptions was to develop alongside classical mechanism, but it was to remain in the background until it could manufacture its own special compromise with infinity. Indeterminism showed its great strength by disallowing the straightforward conclusion that the data from the telescope and the microscope warranted an assumption encompassing infinity in both directions. It was left to systems philosophy, actually present in one form or another ever since the evolution of the first ego, to develop the only choice possible under such circumstances. Ever adept at overemphasizing the internal as opposed to the external, systems philosophers gradually overcame the tremendous lead of the classical mechanists, who overemphasized the external as opposed to the internal. Prospects for microscopic infinity grew, while those for macroscopic infinity withered. Inevitably, the universe, too, again would be viewed from a system-oriented perspective. The whole universe, even though known to be billions of light years in extent, was to be viewed in isolation, a system without an environment. 20th century science admitted the systems evolved, but, as I have explained under complementarity, it was reluctant to acknowledge the full impact of the environment. From the system-oriented point of view, the universe had to be finite. At the same time that science was leaning toward microscopic infinity, indeterminism was pressing for a return to macroscopic finity. Systems philosophy found the way. To understand why systems philosophy was so successful in preparing the accommodation, we must recall the great theoretical revolution initiated by Heisenberg. From Democritus to Laplace, it was possible to advance the cause of determinism by assuming microscopic finity along with macroscopic infinity. But as we have seen, the Laplacian form of determinism is clearly unworkable. Its underlying assumption of finity is no longer compatible with the other assumptions of science. No longer could classical mechanism, based on this form of determinism, seriously propose that the ultimate constituents of matter eventually could be described in full. No longer was there any hope of realizing Einstein's dream of discovering the elementary laws by which the universe could be built up by simple deduction. According to causality and uncertainty, partial descriptions and fallible predictions are the only attainable reality. As mentioned, through the Copenhagen interpretation, systems philosophy was able to distort the true meaning of the overthrow of Laplacian determinism. It did this by borrowing from classical mechanism the notion that a complete description was possible. One only had to consider chance as a singular cause. Systems philosophy was thus ambivalent even toward microscopic infinity. It could refuse to take Bohm's subquantic states seriously, even as it led the search for smaller and smaller particles. Systems philosophy leaned toward microscopic infinity just enough to switch theoretical attention from the external to the internal, just long enough to overthrow macroscopic infinity. The new focus was quite sufficient for the crowning achievement of systems philosophy, the Big Bang theory of the origin of the universe. The ambiguities introduced by the modern attempt to make microscopic infinity compatible with macroscopic finity are no easier to live with than the ones devised by classical mechanism to do the reverse. Both approaches ultimately ended up supporting a grand finity, even in the areas in which they chose to specialize. In actuality, of course, microscopic infinity logically implies macroscopic infinity, and vice versa. This follows from many of the previous discussions, particularly the one on space-time involving the opposed concepts of ideal solid matter and ideal empty space. Again, if we grant these to be merely idealizations, then we are assuming that they have no actual existence. Neither indivisible matter nor immaterial void is possible, although each portion of the universe reflects both to varying degrees. Without actually existing indivisible matter, there can be no microscopic finity, just as there can be no macroscopic finity without an actually existing immaterial void outside the universe. The upshot? The non-existence of the universe is impossible. We can no longer merely entertain either microscopic or macroscopic infinity. We must steadfastly assume both. The resulting assumption of infinity, the proposition that the universe is infinite both in the microscopic and the macroscopic directions, is the only form compatible with causality and uncertainty. Such an assumption is not to be taken lightly, as the struggle over causality and uncertainty indicates. There is, of course, an unavoidable necessary circularity to the argument for infinity. This is a characteristic to be expected if the universe was truly infinite, and assumptions rather than absolute presuppositions, or a priori, were necessary for its study. Because it includes the macroscopic as well as the microscopic, infinity stands out so strikingly different from the currently accepted view that it leads, as we have seen, to a major reinterpretation of all our scientific assumptions. Now, let us examine some of the factual evidence upon which the belief in infinity rests. Quest for the ultimate particle. The ultimate particle has been the object of a continuous search ever since Democritus proposed it 2,500 years ago. In his view, the ultimate constituents of matter were atoms, hard little balls filled with an inert substance called matter. These atoms were unprecedented in that, unlike other things, they could not be further subdivided. Also, unlike other things, all atoms had identical properties. The atomic concept, of course, was useful. Matter does appear to consist of discrete particles. The atom was considered the basic building block of matter well into the 19th century, before its supposed unchanging nature came under question. As more and more information on atoms was accumulated, it became obvious that all atoms could not be considered identical, as the atomist assumption of microscopic finity demanded. True, the basic properties of the constituent atoms of a metal such as gold appeared identical, but the atoms of gold and the atoms of other elements differed in many ways. For example, 1,000,000 atoms of gold did not weigh the same as 1,000,000 atoms of silver. How could the atom be the ultimate particle if different atoms had different masses? There must be something inside these atoms. Perhaps this something was the ultimate particle instead. Sure enough, by 1897, J.J. Thomson had discovered the electron, proving beyond a doubt that the atom was divisible. This began a long series of discoveries that alternately raised the possibility of microscopic infinity whenever a subatomic particle was split, and lowered it whenever there was a failure to split. To this day, each subatomic particle, when explored with some newly invented technique, eventually yields still another even smaller particle. The electron has been succeeded by the quark as the smallest subatomic particle. Will there be an end to this succession? Will an ultimate particle be found? One scientist felt sure that matter is not infinitely divisible, while another reiterated that no ultimate individual or partless particle is known to science. Indeterminists can assert that the electron does not have other particles inside it, while determinists can just as dogmatically assert that the electron is just as inexhaustible as the atom. In the specific, determinists always win out. There are now at least 3 different kinds of electrons, some of which emit neutrinos. But who would be so foolish as to declare that this will always be the case? There can be no end to the debate between those who believe in microscopic infinity and those who do not. There is no experiment that could settle the question once and for all. Looking for the edge of the universe. As we grow up, we find that there are no limits to our environment. Every door opens on another, and another, and another. The intellectual growth of humanity has followed a similar pattern. Our acknowledged environment has expanded from the village, to the continent, to the Earth, to the galaxy, and beyond. Beyond the 1920s, we thought we lived in an island universe situated within an infinite volume completely void of matter. But then the discovery of other galaxies, over 100 billion at last guess, once again dashed indeterministic hopes that the environment was finite. If there was literally something beyond physics, it had to be at least 10 to the 23rd kilometers away and impossible to reach in less than 13.7 billion light-years. Each time its vision dimmed, humanity faced the ancient metaphysical choice. Either what is beyond physics is physical, or it is not. Today, that choice requires a leap of faith just as much as it did in the past. In some ways, our current ignorance of what lies beyond the reach of the largest telescopes is fundamentally no different from that of the pre-Columbian Europeans who were unaware of the New World. In hindsight, of course, it is easy to point out that those who assumed the environment was infinite in the macroscopic direction were scientifically correct. But is this likely to be true in the future? We can never know for sure. The widespread prevalence of the opposing assumption is proof of that. To avoid macroscopic infinity, indeterminists today follow one of two paths. The first visualizes the known universe situated within and perhaps expanding into an infinite immaterial void. The second seeks refuge in the mathematics of Einstein's four-dimensional finite universe. The simple deterministic alternative to such whimsy requires neither an immaterial void nor an unprecedented geometry. Infinity. Microscopic plus macroscopic. As mentioned, classical mechanism emphasized macroscopic infinity, and systems philosophy emphasizes microscopic infinity. Regardless of the special pleas one can make for one exclusive of the other, the two ideas logically imply one another. The indeterministic notion of the ultimate particle with no thing, or nothing, inside it, is of a sort with the indeterministic notion of a universe with no thing, nothing, outside it. The philosophical purpose of finity, whether it be construed as microscopic, macroscopic, or both, is at some point to call a halt to materialism. On the other hand, the philosophical purpose of infinity is to proclaim the universality of materialism. Describing infinity. Those who support the concept of infinity are often asked to describe, or even to define it. But of course, a complete description of infinity would be a contradiction in terms. As the universe is infinitely varied, it is very likely that only statements of infinite length can be true. The ontological structure of the universe is such that all universal statements of finite length are false. Nevertheless, most any child can begin a model of infinity by stacking blocks in all directions. Any attempt to enumerate the members of a class or to repeat a process endlessly amounts to a primitive model of infinity. The method of simple enumeration, for example, was used by George Gamow in retelling the story about the hotel with an infinite number of rooms. Whenever a new guest arrives, the previous arrival makes space available by moving into his predecessor's room, who in turn moves into his predecessor's room. Each guest advances one room each time a new guest arrives. Thus, the infinite hotel with the infinite number of rooms can always accommodate an infinite number of guests. Planck described infinite time by comparing it to the cooling of a hot iron in water. The smaller the difference of temperature between the hot iron and the water, the slower is the transmission of heat from one to the other, and calculation shows that an infinitely long time passes before an equal temperature is reached. This means that there is always some difference of temperature, no matter how much time is allowed to elapse. As models of infinity, these are typical of the system-oriented viewpoint. They are inadequate because even though they attempt to model processes, the processes invariably occur in isolation and thereby develop a static nature. The same event is repeated endlessly. Note that these descriptions are dependent on the assumption of reversibility. Planck's pseudoscientific illustration is not much better than Gamow's quixotic one. Both amount to a negation of infinity, because for the demonstration to proceed, it must occur in isolation. The essence of infinity, on the other hand, lies in the possibility of relative non-isolation, convergence from the environment. In Planck's example, neither the hot iron nor the water used to cool it could escape the impingement or the diminished impingement from the infinite number of things that lie outside of it. Planck first imagines and then calculates that the water will always be cooler than the iron, but the actual cooling of an iron must occur in a real environment that has a real temperature. As the temperature of the iron approaches that of the water, the impact of even one atom or photon from this environment could increase the vibrational motion of one of the water molecules enough to make the temperature of the water higher than that of the iron. The result? End of experiment. End of within-class infinity. The mathematics to which Planck alluded was no proof of infinity, just as Plato's ideal geometric forms were no proof of their real existence. The success of mathematics, as well as of science, depends on its willingness to assume. In other words, to make a beginning. Only by divorcing itself temporarily from the infinite external world can mathematics or science reach a conclusion. Just as the real world intruded upon Plato's idealism, so does it intrude upon the necessarily finite mathematical physics of today. But try as we may, infinity won't go away. The infinities that occur in QED, quantum electrodynamics, are clearly symptomatic of some profound shortcomings in our understanding of physics. You bet. These shortcomings, of course, are none other than those of systems philosophy itself. Our infinite universe refuses to be jammed into the finite, isolated container we have contrived for it. As explained under uncertainty, no theory can be complete because any particular class of things is susceptible to interference from other classes of things. Whether we recognize our ignorance with formal mathematical symbols or in some other way, we still must recognize it. We invariably give up contact with the real world whenever we use mathematical axioms that somehow avoid the concept of infinity. When it deals in specifics and ignores the rest of the universe, mathematics forces thought into the finite mode. When it deals in generalities and slips from its disciplined course, mathematics regularly runs into the notion of infinity. Well-trained minds of the 21st century persist in the grooves provided by systems philosophy. Subconsciously, they know that if